Hello, welcome to the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And this is the part 7 in a little mini series that I'm calling One-Way Fixed Effects ANOVA. And more specifically, this is the art illustration of part 7, where we introduce the concept of contrast. Now, this is under the assumption that you've watched the first 6 parts, and we're going to load the video and run it and have those commands ready for part 7. But this is dealing with an example from Montgomery, the book Design and Analysis of Experiments. It's a 3rd edition, and it's example 3.1, where they look at the tensile strength of fabric. And in the fabric, they use different percentages of cotton in the fabric, and then they look at the tensile strength. And tensile strength means they start pulling it apart and see how much force is required to rip it or pull it apart. And they use 15% cotton in one fabric, and 20, 25, 30, and 35% cotton in these different fabrics. And that's the experiment. So let's run that and then zoom down to contrast. Now, contrast is a linear combination of the beta vector. Now, remember, the beta vector in the one-way fixed effects ANOVA is mu, tau 1, tau 2, tau 3, etc. And in this example, we have 5 treatments. The 15% cotton blend, the 20%, 25, 30, 35. And a contrast is a very specific linear combination of these beta parameters, where the first component is 0, and the remaining 5 components are such that they sum to 0. And then that's called a contrast. And in the video we showed that every contrast of this form is estimable. Remember, in design of experiments, estimable is such an important topic. And to be estimable, we have to show that the lambda parameter here, or in R we call it L, can be represented as a linear combination of the row space of our design matrix. And that's what we want to do first. So we're going to look at these two contrasts, lambda 1 and lambda 2, and they are contrasts because the components sum to 0. The first component of lambda is 0. Now, I must admit, most people, when they look at contrast, they leave off this first component of 0, and they only look at the the C1, C2, etc., where it grabs the tau parameters. But I'm leaving it on to illustrate that this is really a linear combination of all the beta parameters, but in a unique way, where the first component is 0 and the remaining components have to sum to 1. Now, to show that it's a linear combination of the row space of X, we need some sort of row parameter. So here's row 1, and in the video we show that there's an infinite number of rows that would satisfy this. Well, if it satisfies it once, then it's an infinite number that would continue to satisfy. But if you pick a very specific format, then it makes everything easier. And I'll even bring this up in a second. But what you do is you take the first C, you rep, and so that's the L1, the second component. You rep it, you take it divided by 5, and I repped it 5 times. And then you take the, it'd be the third component, but the second, constant in the contrast, divided by 5, repped 5 times, etc. So that's what we do, is we create the row 1 and row 2 in that unique way. And then we note that when we take the the row transpose times X, which creates that linear combination of the row space, we get our lambdas back. So here's the first one. This is essentially 0, 1, 2, negative 5, 2, 0, which is what this is. And they add to 0. The second one, 0, 1 half, negative 1 half, 1 half, minus 3, 2, 1. So these lambda parameters are part of the row space. And it turns out every contrast is. Now, any row that satisfies this condition, that where it's a linear combination of row space and you get that lambda parameter back, well, if you take m times that row, then you get a very specific row back. And matter of fact, any row, I mean m row 1, m row 2, m row 3, that all equal that lambda 1 parameter, you get a very specific row back. And that very specific row or format is what we created. So we should get it back when we multiply these. And we do. And so this is, 1/5. Well, let's look at these rows here. So yeah, so this is row 1, and this is row 1 that we created. Well, this is m times row 1, and they are equal. And then that row 2, and then this is m times row 2, and they are 100% the same, as they should be. Now, let's derive the unique least squares estimate for lambda beta tilde. Well, that is the unique least squares estimate. Lambda beta tilde is the unique least squares estimate for lambda beta. And so here is our lambda, and here is the least squares estimate. So it's x transpose x, generalized inverse, x transpose y. And then L prime is what we did, and we get negative 4.2. So that's our least squares estimate of that contrast, the L1. But we also derived that it's equal to the combination of the group means using the lambda parameter, or the contrast. So each contrast, C1 times the group mean of 1, C2 times the group mean of 2, etc. Those should sum to the least squares estimate also, and that's what we're showing here. So that, here's the group means, right? So this is the treatment 1, where we had a 15% blend of cotton, 20%, 25, 20, 25, 30, 35. But we also showed there's other formats. So we could take row, we're up here. We could take row 1 times m times y, and that also should produce the least squares estimate, and it's negative 4.2, so it does. And then this row transpose m is actually just row transpose. So in our case, because we picked that very specific row 1, so we get it back. But m times y creates that treatment mean vector, so we could just use it and we get it back. Now L2, we create the least squares estimate for L2 beta, and then which the least squares estimate is L2 times beta tilde, which is this. And then to show that it is that linear combination of the group means, it's 4, so we get it back. And then each of these different specific forms, they all equal 4. Now, an estimate of the variance is the sum of the CI squareds, and that's what this first piece represents. We take the lambda parameter, square each component, and sum it. And then take it times an unbiased estimate of the error variance, so that's mean squared residual, and then divided by n, which is the sample size that we for each treatment. So it's 54.808. So that's the error variance. And then we showed there's equivalent matrix representations of this, and each of them involve the unbiased estimate for the error variance. That's what this mean squared residual means. And here we take m row and times m row, and we get the same. And this is just row 1 transpose m row, and we get the same. And here's another form, and all those are the same. And we covered those in detail in the video. And now for the second contrast, we go through the same, and in each case it's 23.37 for each. And so each form is the same. Now in the next video we look at part 8, where we assume that the contrasts are, have a distribution. We assume that the y's are normally distributed, or the error term is normally distributed, and then we can start doing f-tests and p-values, and this will be part of the ANOVA table the next time. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like it, subscribe, and don't miss so you don't miss the next one. Thanks. Bye.